Hello everybody, welcome to the video lecture for Wednesday, March 25th. This is our second video lecture for our newly online Calculus 2 class, our second lecture after our spring break. If you have not had a chance to look at the first lecture, that's the lecture for Monday, March 23rd, I would really strongly encourage you to go take a look at that for a couple of reasons. Number one, that lecture talks about areas of surfaces of revolution, and that's the subject of this homework that is due on Tuesday, March the 31st. See if I can turn that off. I accidentally started that. So that's the homework that's due on Tuesday, March 31st. That should be the next homework assignment that you'll be working on. This homework assignment on volume was actually due already, right? If you're watching this video on after March the 25th, then this homework on volume that was assigned before spring break, that has already been submitted. However, it's possible you might be able to get an automatic extension for that homework, right, if it's not too many days after March 24th, after the due date for that. Recall, as you know, right, you can ask for automatic due date extensions, right, for your homework. The instructions there are in the WebAssign announcements on the right-hand side of your WebAssign homepage. Okay. The other reason that you should be looking at that lecture for Monday, March 23rd, the first video lecture after the break, is I'm talking a lot in that video about how the course is going to proceed from now on, right? How our work is going to be done, how tests will be taken, and things like that. Okay, important just procedural announcements, right, for how the course is going to work. So I think you should also look at that lecture for Monday, March 23rd, also for that reason as well. Okay. However, just as a quick update, right, most of the stuff that is in that lecture you can also find in the announcements that I've been posting in Blackboard and also in WebAssign. Those have also been going to you as email, so I hope you've been reading your email. Probably you have if you're watching this lecture, right? Okay, so this first announcement just is the announcement that we're going to be going online for the remainder of the semester, right? All of our work will be done online, remotely online, and this announcement includes this link to this addendum to the syllabus. This is not a complete addendum, but it does just contain just the necessary information for right now for how the class is going to operate, right? Okay. So if you haven't had a chance, make sure you take a look at that syllabus addendum. It's pretty short, you know, just will give you sort of you know, kind of key information that you need, right, to get started here on the remainder of the semester. One important thing that I know you're thinking about that's in this syllabus addendum is how tests are going to operate, right, since we're not meeting face-to-face any longer. Basically, the tests will be take-home tests, right, that I'll be posting on Blackboard, and you'll be writing down your answers to those, and you'll be scanning your answers and emailing those back to me so I can grade them. So that's essentially how testing is going to work. Of course, our homework assignments will still be carried out in WebAssign like they were before spring break, right? Okay. Along the lines of the test, we will not have our first test until April 10th. So it was originally scheduled the next test for April 1st, but clearly we're going to have some time to regroup, right, and sort of get accustomed to how the course is going to work from now on. So our next test will not be until April the 10th. And again, that's going to be that'll be a take-home test for which you'll be mailing me your answer. So we have more time to prepare for that before that test is actually done, but that's basically how it's going to work. Also now, in terms of being able to ask questions and contact me, I do want to remind you that you can always email me, right, at my regular university email address, and you can also call me at my office phone number. Although campus is closed now, and that's unfortunate. It's unfortunate because you won't have access to the campus, so you will not have access to computer labs on campus. But you can call me at my campus phone number, and those calls will be forwarded to me. So I'll be able to answer those live, all right, and talk with you, or you can leave a message and I can call you back, right? So if you have any questions at all, please make sure that you are contacting me, right, so that I can help you with those questions. In particular, if you are having hardships, and it's possible that you might, right, with these really terrible circumstances that have developed. Please make sure you contact me so I can give you what advice I can about how you can deal with those hardships, at least with respect to this course, right? So what your options are with respect to the course if you're dealing with some sort of issue that's going to prevent you from, or going to make it difficult for you to complete the class, all right, online. Also now, I'm also going to be conducting my office hours now, of course, which used to be in my office face-to-face, but I'm going to be conducting those now via Zoom sessions, right? And again, in this announcement, there are the instructions for joining those Zoom sessions, so you can ask me questions during my office hours. I have office hours every day of the week, and here are the instructions for joining those meetings. Okay, so if you need to ask questions, right, particularly about the homework, make sure that you either, of course, you may choose Ask My Instructor from WebAssign, but you can also join me during my virtual office hours, okay, and ask me questions at that time. Now, a great advantage that we have in this class is that Taylor will still be able to conduct her SI sessions. She has posted a message on an announcement on Blackboard with instructions for how to join her SI sessions, which are also going to be conducted via Zoom. And those are going to be held during what used to be our class time, right, which is 1 o'clock on Monday and Wednesday. So I think they're going to be 1 to 2 on Monday and Wednesday during our old class time. So you can read Taylor's announcement in Blackboard and then join one of her SI meetings, right, via Zoom. So you can talk with Taylor and also get help from Taylor as well. So that's a really nice thing that we have in this particular class that other classes are not going to have. Just a general reminder here, remember, be sure you are reading all of your email, okay? So I know you're going to get bombarded with email from all your courses, but make sure you're reading your email, because that's really the only, really one of the only ways I have to communicate with you now, right, since we're not seeing each other face-to-face. So please be careful to read your email. Be sure to read announcements that are made in WebAssign, and those same announcements are made in Blackboard, so make sure you're reading the announcements in Blackboard as well. I think when I make those announcements, they go to you as email, but they remain as announcements in Blackboard, posted in Blackboard. So make sure that you're keeping up with these announcements, right? Okay, so I think that sort of covers, right, kind of just the procedures for the class, right, the operations for the class. I want to now jump right into talking about our next topic in the class, and we're going to go back to now integration and learning some new integration techniques. So for the past few weeks we've been talking about applications of integration, like solving differential equations or computing volumes or surface areas. But now we're going to go back to learn some more advanced integration techniques, and the one that we're going to learn about today is called integration by parts, and that is a really important technique. So that's a really crucial topic in the class. This is one of the topics in the class that you're likely to see revisited in future classes. All right, so please try to devote some attention here to learning how to do integration by parts. Okay. That's what we're going to talk about right now. Actually, I have not posted the assignment yet, though, for integration by parts, but I will post that soon. Okay. All right. So again, if you have questions, email me, call me, or visit me during my Zoom office hours, or visit Taylor during her Zoom SI sessions. Okay. All right, so I'm going to talk with you now, right, about the sort of what the idea is behind integration by parts, and it's really a very straightforward idea, okay, where integration by parts comes from. The examples are sometimes a little bit more complex, all right, so the problems are not always simple, but the idea behind integration by parts is fairly simple. So recall now that lots of the integration techniques that we have learned in the class, they are inverse of the differentiation techniques that either we've learned in this class or used in this class, or that you learned in Calculus 1, right? So, for instance, we've used in this class to integrate many times, right, the anti-power rule, right? That's one of our favorite integration techniques. And remember, that comes about as just the inverse, or sort of the opposite of the power rule for a differentiation, okay? And it makes sense, right, that a lot of our integration techniques are inverses of differentiation techniques, because integration, of course, is the inverse operation of differentiation. Another example of this would be the integration by substitution. So if you think about it, how integration by substitution works, right? Integration by substitution is sort of the inverse of the chain rule for differentiation. And today, this new technique that we're going to learn, integration by parts, also comes about by reversing or inverting one of our more useful differentiation techniques, and that happens to be the product rule, right? Okay, so we often use the product rule, right, to differentiate in calculus, and so we're going to exploit that rule to develop an integration technique, and that's how integration by parts actually comes about. It's the opposite, or the inverse, of the product rule, or you can think of integration by parts as kind of being the anti-product rule. Actually, let me write that down, okay, just to emphasize that. So integration by parts is sort of the anti-product rule for integration. Okay, all right. So let me explain how we're going to reverse the product rule to get an integration technique here. All right, so let's recall the product rule. I'm sure you know that really well, right? Because we've used it a lot in the class, and I know you used it also a lot in Calculus 1. But, of course, we use the product rule, right, when we're trying to find the derivative of a product of a couple of expressions, all right? So, in this equation, we're thinking of u and v as not just being simple variables, but being expressions in x, right? Or you can also think of them as being functions of x. So if you take the derivative, right, of the product of a couple of expressions, well, you know the product rule, right? It says first you're going to keep one of the factors but differentiate the other one. So when I wrote this down, I kept a u, and then I took the derivative of v, the second factor, so I wrote that using the dv dx notation, and then plus, right, you just alternate, correct? So in the next term here, you keep the second factor factor, right, fixed, right, so you keep the v, and then I took the derivative of the first factor, and I wrote that down as du dx, right? So that's just the very familiar product rule, right? If you want to, I'm going to convert this for a reason to kind of the more modern notation for derivative, the prime notation for derivative, okay, rather than using the dx notation for the derivative. And so if you write this in the more modern notation, right, you could say u times v prime, right? The derivative of this product is u times v prime, right? Okay, u times the derivative of v, and then plus keep v, and then times the derivative of u, right, which is u prime. All right, now so that's differentiation, right, using the product rule. All right. Now, how can we take the product rule and turn that into an integration rule? Okay. All right. Well, I'm going to do that in a very straightforward way. Okay. Let's think about what happens now when we integrate both sides of the product rule. Okay. So I'm going to integrate both sides of this equation. Let's write that down. So I'm going to take the antiderivative of uv prime, right, and then the antiderivative here of the right-hand side of this equation. All right, now look, because you're taking the antiderivative of a sum, right, so you have the integral of a sum here, you can break this up into this right-hand side. You can break this up into two separate integrals. So let's do that. I'm going to write this as the integral of uv prime plus the integral of v u prime. Okay, like this. All right. So that's kind of my first step there in developing what I'm going to call in a moment here integration by parts. All right. Now, so let's look at the sum of these two integrals now, and I'm going to rewrite them just a little bit, okay? Because look, v prime, of course, right? You know that means the same as dv dx, right? V prime is just another way of writing dv dx. But I can take this equation and I can solve it for dv, right? Okay, so I can write dv as v prime times dx. Oh, I forgot to do something here that I was supposed to do when I took the antiderivative that I just remembered here, right? Remember, when you integrate, you have to indicate, right, what variable you're integrating with respect to. I forgot to do that. That's really important. All right, so we're integrating with respect to x here, so I need to indicate that by writing dx here in my integral. We need that dx. So let me put that back in here. All right. The reason that I need that here is I want to show you something. Again, so let me go back to what I was just mentioning. So we know that v prime means the same as dv over dx, right? So you can take this equation and you can solve it for dv by multiplying both sides by dx, right? So you get dv is equal to v prime times dx, all right? And then likewise, u prime means du dx, so you know if you multiply both sides of this equation by dx, you get that du is u prime times dx. All right. Now, here's what I'm gonna do with that. All right. So let's take that. Let's take now this these two integrals. Right. I'm gonna rewrite them down here, but it's easy to integrate the left-hand side of this equation, right? Because you're just taking the antiderivative of a derivative, right? So the antiderivative of uv prime, the derivative, right, is just going to be uv, right? You're just going to undo the differentiation here on the left-hand side. So when you integrate uv prime, you just get uv, correct? Now, on the right-hand side, you have the sum of these two integrals. But as I pointed out to you just a second ago, right, notice that v prime times dx, that we can write that as dv. So this v prime times dx, I'm going to rewrite this as dv, and this u prime times dx, notice that's the same as du, right? So I'm going to substitute for u prime dx, I'm going to substitute just du. Oh, and this is exactly what I was looking for, all right? So notice I have that uv, right, that original product is the integral of u dv, the antiderivative of u dv, plus the antiderivative of v du, okay? Now, what I'm going to do is move this this integral v du, I'm going to move that over to the left-hand side of this equation. And that gives me this equation that I have boxed in here on the left, right? Notice you have uv minus v du, minus the integral of v du, I should say, is equal to the integral of u dv. Right? Again, all of this is just a consequence of the product rule, right? Just integrating the product rule. Now I'm going to switch, just to make this equation easier to use, I'm going to switch the left hand and the right hand side. So I'm going to write this as u dv first on the left hand side. I'm sorry, integral of u dv on the left hand side is equal to I'm going to pull this to the left-hand side, and then that's equal to uv minus the integral of v du. So these two equations are the same. I just switched the left and the right-hand side. All right. This is, finally, this is the equation that I was after. All right. That is called the integration by parts formula. All right. Notice you have integral of u dv is equal to u times v minus the integral of v du. Or you can think of this equation also as the anti-product rule. That is the integration formula, the integration rule that we're going to derive from the product rule for differentiation. This is sort of the reverse of the product rule for differentiation. Okay, now, all right, this all looks kind of abstract, right? Until we actually apply it to an example. It's not quite clear how this this particular formula is useful, right? So we're going to do an example right now. But this is the integration by parts formula. This is the formula that you want to memorize to use integration by parts. And again, you can think of this as the anti-product rule, right? That integration by parts formula comes about by taking the reverse, right, or the inverse of the product rule for differentiation. Okay. Now, we have to look at an example because this sort of is meaningless until we see an example, right? So, so let's see how to use this. All right. So here's our first example. We're going to try to now find the antiderivative of x times e to the x. This is an antiderivative that we have not been able to find so far in the class. All right, so we have not been able to do this up until this point, okay? But it turns out that the anti-product rule, or the integration by parts formula, is exactly the tool that will allow us to integrate this expression x times e to the x. So you're not going to be able to integrate this by substitution. You're not going to be able to integrate this by using the anti-power rule, but you are going to be able to integrate this by using integration by parts, or the anti-product rule. So here I've rewritten the integration by parts formula just to remind us of what that integration by parts formula is. All right, look, to use the integration by parts formula, right, you're going to use that when you have, again, an integral that you're trying to integrate, right? But to use the integration by parts formula, you have to pick out, right, from the problem that you're given, you have to pick out what you're going to label as u, right? So sort of what you're substituting u for here, and what you're going to label as dv. That's really the key parts of using integration by, that's really the key step, I should say, of using integration by parts, is when you're presented with an antiderivative of integral you want to solve using integration by parts, right? Okay, you have to pick out what you're going to call u, which part of the integral you're going to call u, and which part of the integral you're going to call dv, okay? That's easier said than done. All right, but I'm going to show you now two different guidelines for how you can make that choice. Okay, but it's not completely cut and dried, so sometimes you have to do a little bit of trial and error, right? That is sometimes involved in doing integration by parts, okay? You have to do a little bit of experimentation. But we do, not that much, because we do have some guidelines that can help us with choosing which part of the integral you want to call u and which part of the integral you want to refer to as dv, okay? All right, let me show you what those guidelines are. Okay, all right, so these are just taken right from the book. Actually, now I have a different set of guidelines, okay, that I'm also going to show you in a later problem, okay? So we actually have a couple of different techniques that we can use to decide what we're going to call u and what we're going to call dv. All right, so here's what the book says, though. All right, let dv be the part of the integrand that is easy to integrate. Okay, so always pick dv to be the part of the integrand. It doesn't have to be the whole integrand, right? The part of the integrand that's easy to integrate. Okay, so if you can pick out part of the integrand that's going to be easy to integrate, that's what you're going to call dv. If it's not easy to integrate, you're not going to want to call that dv. Okay, you'll see why here in just a second. And finally, now also you have to choose the u as well. And so what the book says is, let u be the part of the integrand where when you differentiate it, you get a simpler expression, right? So, you know, sometimes when you differentiate an expression, oftentimes the derivative will be easier than the original expression, right? It will be simpler in some sense than the original expression. But sometimes that's not true, right? Sometimes when you differentiate an expression, you get a more complicated expression than the original expression. So you want to see if you can pick out part of the integrand so that when you differentiate it, you get a simpler expression. If you pick out part of the integrand where you integrate it and you get a more complicated expression, that's probably not a good choice for u, right? You're going to let u be the part that's not easy to integrate, but when you integrate it, it gives you an easier expression. All right, let's see if we can practice these guidelines on this particular problem. All right, so remember we had x times e to the x dx, right? That's what we were trying to integrate. So we actually have lots of choices here, right, of u and dv, depending on how we want to break this up. So remember, what we're integrating is x times e to the x, right? So I guess the first thing that you could think of here is you could let u be the x, right? Let u be just the x part here, and then let dv be e to the x dx. By the way, when you choose dv, it's always going to include the dx. dv always includes the dx. Now, let's see. Does that match our guidelines, right? So remember, you want to pick u, right, so that when you integrate it, you get a simpler expression, and then you want dv to be something that is easy to integrate, or that at least you know how to integrate. Maybe it's not easy to integrate, but at least you know how to integrate that, okay? All right, so we're going to start with experimenting with this choice for u and dv first, but let me show you what some of your other options would be here, right? You could let the u be the e to the x, and you could let dv be the x dx, right? That you could switch the x and the e to the x here, and you can think of u as being e to the x and dv as being x times dx. Or you could think of u as just being 1, right? You could think of u as just being 1, And then you could think of dv as being x times e to the x. So you have a coefficient of 1 here that's kind of invisible, right? Okay, so you could think of u as being 1 and then dv as being x times e to the x. Or your other option here is to let u be x times e to the x, and then you could let dv just be the dx. Okay, remember dv always is going to include dx. All right, so lots of options here for the u and the dv. All right, let's see what's good about that first option. So let's let u be x, and then let's let dv be e to the x dx. So let's see if that meets our guidelines. All right, so first, if u is x, right, if u is x, then what's du dx going to be, right? So if we let u be x, then that means du dx is just 1, right? Oh, that's great, okay? Because that is right, 1 is certainly simpler than x, so that means when you differentiate u, right, you get a simpler expression than originally u originally was. And that's what you're looking for, right? Or at least that's what the guidelines say that you're looking for. All right, now, if we let u be x, right, that means that, remember, that means we're letting dv be e to the x dx. And that is going to be a good choice if this is easy to integrate, right? Okay. All right, well, let's try integrating then dv, okay? So if you integrate dv, right, that means you're going to integrate e to the x dx. But as you know from before the break, right, it's very easy to integrate e to the x dx. In fact, it's just going to be e to the x, isn't it, right? When you integrate e to the x, you'll just get e to the x. And so, see, that means that this choice for dv is very easy to integrate. So if you let dv be e to the x dx, that means you're going to be that's going to be easy to integrate. By the way, you know when you integrate dv, right, you're going to get v, okay? So here we know something. We know that v is e to the x. So, those choices for u and dv, right, they seem to match our criteria, right? If we let u be x, then the derivative of u is just 1. That's simpler than u. And if we let dv be e to the x dx, that's easy to integrate, okay? Because e to the x, when you integrate that, you just get e to the x. So that's very easy to integrate. And so we know here, by the way, when we integrate dv, that's v. So we know now that v is e to the x. All right, so let's use this choice for our integration by parts. Let's use this choice there in our integration by parts formula. So remember, here is the integration by parts formula, right? It says the antiderivative or the integral of u dv is u times v minus minus the integral of v times du. Okay, so there was our original problem, right? We were thinking of u as being x. We were thinking of dv as being e to the x dx, right? So our integration by parts formula says this antiderivative is going to be, it's going to be u times v. Well, of course, u is x, right? And what is v? We know what v is, right, though, correct? Because remember, you know, don't forget, you know that v is going to be the antiderivative of dv, but we said dv was e to the x dx, right? But we know what that antiderivative is. That's just e to the x. So we know that v is going to be just e to the x. So I can fill that in now to my integration by parts formula, right? Now it's minus the antiderivative or the integral of v, but again we know v is e to the x power, right? So it's the integral of e to the x, and then times du. Now, we do have to know what du is, all right? So let's remind ourselves of that, okay? We wrote this down just a moment ago, but let me repeat it. Remember, we were assuming that u is equal to x, right? So du dx is equal to 1, and that means, if you multiply both sides here by dx, that means that du is equal to dx. Oh, so we can fill in for du, we can just fill in dx, right? Just like this. All right, so we've made some progress here. It doesn't look like it, but we have made some progress here. Let me show you. So remember, we were trying to integrate this expression, right? X e to the x dx. So now we know by our integration by parts formula, this is x times e to the x minus the antiderivative of e to the x dx. Now, we're not quite finished here yet, right? Okay, because we haven't quite found yet the antiderivative, the integral of our original expression. But we're almost through, because this integral is easy to calculate, right? What is the antiderivative of e to the x? Ah, we know that, right? That is just e to the x. So there you've got it. Don't forget to add on your arbitrary constant. Ah, there's the answer to the original problem. The antiderivative of x e to the x dx, which we could not integrate before, that antiderivative is x e to the x minus e to the x plus a constant. So see, we did that. So we now know how to integrate something that we did not know how to integrate by before, using this integration by parts formula, which is the same as the anti-product rule. All right, let's try that process again, but I'm going to show you now what's going to go wrong if you make a bad choice for if you make a bad choice here for u and dv, right? Remember, that's what you have to pick, is what is u and what is dv, all right? Out of your, remember, this is the original problem, right? We wanted to integrate x e to the x. So suppose instead of letting u be x, suppose we let u be e to the x power, right? Okay, so we chose u to be this part of the integrand. And then that means dv is going to be the rest of the integrand, right? Remember, after you've made your choice for u, then everything else has to be dv. So, or vice versa. If you make your choice for dv, then everything else has to be u. But since here we chose that u is going to be e to the x, that means then that dv is going to be x times dx, because that's what's left, right, in the integrand, right? Okay, so let's see now if this is going to work. Okay, so is u easy to differentiate, right? Remember, you want u to be not that u is easy to differentiate, but you want the derivative of u to be no more complicated than u. So let's see, if you take the derivative of u with respect to x, right, you get, well, what's the derivative of e to the x? You get e to the x, right? Well, that's pretty easy, right? There's u, and there's its derivative. E to the x is no simpler than e to the x, but it's not any more complicated than e to the x, right? If you multiply both sides here by dx, you'll get that du is equal to e to the x times dx. All right, now, let's see. Suppose now that dv was x dx, right? So remember now, our choice of dv, we want something that's easy to integrate, right? Because when you integrate dv, you're going to get v back again, correct? So let's see what happens when we integrate dv. This is dv, right? So when you integrate x dx, well, that's not too hard to integrate, right? That's going to be x squared over 2. So v is x squared over 2. So that doesn't seem all that bad, right? So let's try plugging this in to our integration by parts formula, right? So our integration by parts formula says, remember, what does it say? Okay, it says what your original integrand here, remember, that was u dv, right? Okay, see here you have the antiderivative of u times dv. Well, that is equal to u times v, so that would be e to the x, there's u, right, e to the x, times v, there's v, we got v by integration, right, so that's x squared over 2, minus, and then it's the antiderivative of v, which is x squared over 2 times du. But remember, du is e to the x dx, right? Because du dx was e to the x, so multiply both sides by dx, you get du is e to the x times dx. So there's du, okay? So we can fill in the integration by parts formula here, right? u dv is uv minus antiderivative of v du. But the problem here is we're going to get stuck, because to finish off the problem, we have to be able to now integrate x squared times e to the x. And unfortunately, we don't know how to do that. Okay, so we really are stuck at this point. We don't know how to find the antiderivative of x squared over 2 times e to the x. So all that tells us is that this choice for u and dv, for this same problem where you were trying to integrate x times e to the x, this choice for u and dv just didn't get you anywhere, right? Okay, it just wasn't a useful choice. Our first choice for u and dv, that worked because we were able to get our antiderivative is x e to the x, right, minus e to the x plus c. But when we tried this choice for u and dv, unfortunately, we weren't able to complete the process because we could not find this antiderivative. So that illustrates the fact that when you're using integration by parts, the choice of u and dv is really crucial. That's what's going to allow you to actually use the integration by parts formula. All right, well, that's only one example, so let's try another example. And again, of doing integration by parts. So here's the integration by parts formula, right? Again, that tells us if you have an antiderivative that looks like this, u times dv, right, where you get to choose the u and you get to choose the dv, that is equal to u times v minus the antiderivative of v times du. And what makes this formula useful is sometimes, or you're hoping, this antiderivative is easier to compute than the original antiderivative was, right? Okay, that's what makes integration by parts useful. Okay, let's go through just all the steps of integration by parts one by one. Okay, and when you're actually using integration by parts in your homework problems, you'll be able to, after a few examples, you'll be able to go through these steps much more quickly than we're doing them here. I'm just trying to do them one step at a time, just so that you'll learn the steps. But when you actually start practicing this, you'll get really fast at this. Okay. All right, so suppose we want to, here's another antiderivative that we cannot integrate up until this point. So suppose we want to integrate x times the natural log of x dx, of course, right? All right, so if we're going to try to do this using integration by parts, okay, then we have to find the u and we have to find the dv, okay? So that's really the key step. All right, so remember, you want to choose u, right, so that the derivative of u is simpler than u, and you want to choose the dv so that you can integrate it, okay? Because you have to integrate the dv in order to figure out what v is in the integration by parts formula. All right, so let's see what looks like a good choice here for what looks like a good choice there for u and dv. Do not, I mean, sometimes this works, but just don't think you're going to start reading the expression from left to right, and don't think that the first thing that you see there is going to be the u, and the second thing is going to be the dv. I mean, I guess that's kind of the naive choice there, right? But that may not always be the correct choice. In fact, I think if you let u be x squared and you let dv be natural log of x dx, that's not really a very good choice. Not because of the u, but because of the dv. All right, let me show you why here, and then we'll go back and we'll maybe try again and get the right choice. Okay, so if you let u be x squared, that when you differentiate that, that's nice because the derivative of x squared is 2x, so that does give you a simpler expression than x squared, right? I guess most people would think 2x is a simpler expression than x squared, right? So, all right, so that's okay, right? When we differentiated u, we got something simpler than what we started with. But here's the issue, right? We need to be able to integrate dv, because when you integrate dv, that's how you find v, okay? But to integrate dv, that means we have to be able to integrate natural log of, x dx. And we do not, although natural log of x is a simple function, right? I do not think we have learned yet how to integrate natural log of x, okay? We do not know how to integrate that. We know how to differentiate natural log of x, right? But we do not know how to integrate natural log of x. So this is not the right choice for u and dv. That's my point, okay? All right, so, but that's okay. We can go back to the drawing board here, right? And there's lots of other options there for u and dv. So we can try something different here, correct? So what I'm going to try the second time now is for u here, let's let u be natural log of x instead of x squared. So I'm going to let u be natural log of x. And then, right, so let u be natural log of x. And then, of course, dv is going to be everything else because that's your only option, right? So if u is natural log of x, then dv will be everything else. That would be x squared dx, right? All right, so let's see how this works out. So first, let's try differentiating u, right? And when you differentiate natural log of x, that's easy to differentiate, right? You just get 1 over x. And I think most people would say 1 over x is a simpler expression, right, than natural log of x. So we sort of met the guidelines here, right? The derivative of u is easier than the original expression u. Now, you notice that in the integration by parts formula, you don't want du dx, you want just plain du. So take this equation and solve it for du. That's pretty easy to do, isn't it? Because all you have to do is multiply dx by both sides. So you get du is equal to 1 over x times dx. That's what du is equal to. All right, now let's try finding v. We also have to know v, right? Because that is useful in the integration by parts formula. We already know u and we already know dv, right? But we don't know what v is. All right, so our choice for dv was x squared dx, right? dv is x squared dx. So when you integrate dv, that means you're going to be integrating x squared dx. But also when you integrate dv, that gives you v. So that's how you figure out what v is, right? That you need in your integration by parts formula. You have to integrate dv. But that means here that you're integrating x squared dx. But that is easy to integrate, thank God, right? Okay, because that we can integrate just using the anti-power rule. So that's just going to be x cubed over 3. You don't have to add the constant here yet. Okay, we can save adding the arbitrary constant till the very last. All right, so just write the antiderivative of x squared as x cubed over 3. So now we know what v is, right? Now we are making progress. So actually, let's go ahead and use now our I'm going to skip some of these steps that I had listed here. Now that we know what v is and now that we know what du is, let's go ahead and apply our integration by parts formula just immediately here, right? So we know that the antiderivative of x squared, natural log of x dx, right? That is u times dv, right? Is equal to u times v. So u was natural log of x, right? Times v, but we figured out what v is, right? v is x cubed over 3, and then minus the antiderivative of v, which was x cubed over 3, times du, right? du. But du is 1 over x dx. Oh, so nice, right? So we have, let me write the x cubed over 3 first here. So we have x cubed over 3 minus, and then let's see, what does this antiderivative simplify to? X cubed over x will reduce, right? That is x squared over 3 dx, right? X divides into x cubed, it leaves you with an x squared. So all we have left to do to finish off the problem, all we have left to do is just find this antiderivative of x squared over 3, and that we can easily find that antiderivative just by using the anti-power rule, correct? Actually, first, let me factor out a 1/3, right? And that would leave me with the antiderivative of x squared dx. But x squared is so easy to integrate, right? Because we can integrate that using the anti-power rule again. Oops, I forgot. I forgot to write in this natural log of x here, so let me make sure I put that back in. And so let's see, what is the antiderivative of x squared there? Well, you know that very well, right? That's going to be x cubed over 3, right? And then don't forget, now we're going to add our constant. Oh, wow. So let's see, what does this end up being? So we get natural log of x, right, times x cubed over 3 over 9, right? So 1/3 times x cubed over 3 is x cubed over 9, and then plus this constant. So I finished the whole problem already right here, right? Okay. There is my derivative, see? That's a pretty challenging antiderivative, I think. So the fact that we can find that antiderivative, wow, that's pretty good. Okay, I think we've really increased our knowledge there quite a bit already. So, so I hope you sort of understand the steps there a little bit better of integration by parts, right? Okay. So when you're going to use integration by parts, right, you're going to break your integrand right into a u and a dv, and then you have to find a du, right? Okay, because that's part of the integration by parts formula, and then you also have to find v. Right, you do that by integration because that's also going to be part of the integration by parts formula. And once you found the du and the v, then you can fill them into this integration by parts formula. And then the last step is to see if you can find this antiderivative, the antiderivative of v du. And if you've chosen v and u carefully, then you'll be able to find this antiderivative. This antiderivative will be much easier than the original antiderivative if you've chosen the u and the v properly. Okay. Well, we still have some more examples to do here. All right, so we'll get a little bit more practice here with this. We'll get a little bit more practice here with this integration by parts. Okay, let me see. Let's see if we can scroll down here now to our, where's our next example? Oh, here it is. Okay. Yeah, this one. Whew. Looks terrible, doesn't it? Now we want to find the antiderivative of the arc sine. So we certainly know how to differentiate the arc sine, right? Okay. But now we want to find the antiderivative of the arc sine. Wow. Okay. And we're going to do that using integration by parts. So I'm going to pause here for just a second, and then we'll come back and look at our next examples. Okay, let's see how to apply integration by parts to integrate arc sine of x. So again, we know how to differentiate arc sine, but let's see how to integrate that. I'm now going to show you a second way, a second set of guidelines here that you can use for choosing the u and the dv. And this doesn't always work, but it works frequently, and when it works easily. So this is a very useful technique. This is called the Liate method. Liate here is an acronym, and so that means this word is obviously not really a word, right, Liate, but this word is formed by the first letter of several words, and actually here are the words, right? Log, inverse, algebraic, trig, and exponential. And that sequence of words there is going to give you a guideline for how to pick the u, and then the dv would be everything else in the integrand. So what the Liate method says is that if you have a log function in your integrand, that is what you're going to let be u. All right, and log has precedence. So first look for a log, and if you have a log, then you're going to let that be u. Next, if you have an inverse function in your integrand, then you're going to let that be u. Okay. And then next, if you have an algebraic expression, so that would be something like square root of x or x squared, then you'll let that part of the integrand, let that be u. And then next, if you have a trig function in your integrand, you're going to let that be u. And then finally, last choice here, if you have an exponential function in your integrand, then you're going to let that be u. Okay. So, so in this order of priority, you want to let u be either a log function or inverse function or algebraic function or trig function or an exponential function from your integrand. And again, the first letter of those 5 words there, that gives you the acronym Liate. All right. Okay, so we're going to use this guideline now. It's very easy to apply, so we're going to use that in trying to integrate arc sine of x using integration by parts. So Liate says first look for a log, right? Well, obviously we don't have any logs in this integrand. And then next look for an inverse function, but we do have an inverse function, obviously, right? Because the arc sine function is the inverse of the sine function. So according to the Liate method here, right, you would let actually u be arc sine of x. Actually, almost your entire integrand there is going to be u, right? U is going to be arc sine of x. And what that means is that once you've chosen u, then the dv can only be what's left in the integrand, and that would just be dx, right? So dv is going to be dx. And again, now, once you've made those choices, then it's pretty easy to start, right, the integration by parts process, correct? Okay, so that means we just have to fill in the parts of this integration by parts formula, right? And we've already chosen u, right, and we've already chosen dv, correct? So all we have to do now is to figure out what v itself is, not db, but what v is then, and then also what du are. So those are the next two steps in the integration by parts process. Let's find du, right? All right, so to find du, take the derivative of u with respect to x, right? Here's u, so we need to remember what the derivative of arc sine is, and so I hope you can remember that from before the break, but if you can't, just look it up, okay? So derivative of arc sine is going to be 1 minus 1 over the square root of 1 minus x squared, all right? Which means then that du is going to be 1 over the square root of 1 minus x squared, right? And then times dx, okay? All right, so there's our first step, right? We have now found what du is. Now we have to figure out what v is, right? All right, so, and remember, v is going to be the antiderivative of dv, but dv, of course, we have chosen to be just dx. So you just have the antiderivative of dx, and that's pretty easy, right? Okay, because of course dx is really 1 times dx, and so we're really just integrating 1 here, and that is just going to be plain old x. Oh, so v comes out to be really nice there. That's just going to be v turns out to be really nice there. That's just going to be x. And now the next steps there are to start filling in the integration by parts formula, right? Okay, so we know that the antiderivative of u dv, that is arc sine of x dx, right, is going to be equal to u, right, which we chose to be arc sine of x, times v, which again we found that to be x, right, minus the antiderivative of v, which is x, right, times du, but here is du. It's 1 over square root of 1 minus x squared dx. So if we can just now calculate the antiderivative of x times 1 over the square root of 1 minus x squared, right, then we'll be finished really there with the integration by parts, okay? Now, we may think here that we've gotten stuck, right, because it may look scary there initially to integrate x times 1 over the square root of 1 minus x squared, okay? That's not completely trivial, right? But I think this integral we can do by substitution. So we do not need integration by parts any longer. Okay, so that looks intimidating, but I think this antiderivative we can actually figure that out. All right, so so let's see if we can do that. That's actually listed in the notes here as this step, right? Find this antiderivative of v, right? Okay, this is v, and this, of course, is du, right? So, so let's do that. So the antiderivative of v times du, that's the antiderivative of x times 1 over the square root of 1 minus x squared dx. And again, the reason I think maybe this is not all that bad is because I notice here that if you look at the quantity under the square root, 1 minus x squared, notice its derivative is minus 2x. And here we have an x outside of the square root. So that gives me hope that the integration by substitution is going to work for this particular problem. And what I'm going to substitute for is the 1 minus x squared. Now, usually I would write u equals 1 minus x squared, right, and do that substitution, but I'm using u, that variable u, as something else in this problem, so I'm going to make a slightly different substitution here. Let's use z instead, and let that be 1 minus x squared. So what is dz dx? That's minus 2x, right? And so if we now solve this for dx, I think we get that dx is equal to dz over minus 2x, right? And now let's carry out our substitution. So I have here x times 1 over the square root of z. Remember, I'm substituting z for 1 minus x squared, and then times dx, but dx is dz over minus 2x. Oh, cool. So just like I had hoped, right, the x's will cancel out here, right? And we end up with a pretty simple antiderivative after I factor out this minus 1/2. So I have minus 1/2 times the antiderivative of dz over square root of z, but I can write that as the antiderivative of z to the minus 1/2 power, right? 1 over square root of z would be z to the 1/2 power. And I can integrate that now just using the regular old power rule, right? Okay, so we get a very easy antiderivative here. This is going to be z to the 1/2 power, right? Add 1 to the exponent, right? So z to the minus 1/2, add 1 to that. You get z to the 1/2 power, and then divided by that new exponent, right? Which is, that's nice, that is just 1/2. Well, look now, a minus 1/2 and 1/2, those will cancel each other. These will divide out, because here you're multiplying by 1/2, and here you're dividing by 1/2, right? So those will cancel, but the minus sign doesn't go away. So you end up with minus z to the 1/2 power. But z, of course, remember, was 1 minus x squared. So it looks like after all this is said and done, we end up with minus the square root, 1/2 means square root, right? Minus the square root of 1 minus x squared. Oh, there is v times du. It's minus the square root of 1 minus x squared. Oh, so now we can just fill that in, right, to our integration by parts formula. So we have, don't forget, x, arc sine of x times x. Let me write the x in front. So x times the arc sine of x, right? And then minus this antiderivative, right? But we just calculated that, right? That antiderivative is minus the square root of 1 minus x squared. So I have minus as part of the formula, the integration by parts formula, and then you have also this second minus, right? which came about from this antiderivative. So you have minus the square root of 1 minus x squared. And then now you can add on the constant finally, because we're just about done. So we end up here with x times the arc sine of x plus square root of 1 minus x squared plus a constant. Cool. That turns out to be the antiderivative of arc sine of x. Who would have guessed that? I wouldn't, right? Okay, so antiderivative of arc sine of x is x times the arc sine of x plus the square root of 1 minus x squared plus a constant. And we got that from using integration by parts. Okay, that's nice. Okay. All right, I'm going to show you one more now integration by parts example. We have a couple of integration by parts examples, right? More to go, but I'm only going to show you one in this tape. The next one is a little bit more complex. I mean, the last one is a little bit more complex, and so I want to save that as kind of a warm-up for the next lecture, next Monday's lecture. So that would be Monday, is that April 1st, right? Okay, or March 31st, or March 30th. I'm losing track of days here. Maybe that is March 30th, right? So I'll save that last integration by parts example to begin our lecture on March the 30th, okay? But let's do one more before we're finished here, okay? This one also is a little bit more complex, but not as bad as the last one. I mean, the very last example. All right, so let's see if we can now integrate x squared times sine of x dx. And the reason that integration by parts, when you look at this antiderivative, the reason you might think that integration by parts is helpful here is, notice you have a product rule, right? You have a product of two expressions in this integrand, and remember the integration by parts is the anti-product rule, right? So since you have a product in this integrand, maybe integration by parts will be useful in finding this antiderivative. All right, so, well, let's try it. And remember now we're going to have to pick the u and the dv, and I'm going to use the Liate method again to pick the u. So the Liate method says what? Okay, to pick the u, you will first let u, if you have a log in your integrand, use that as the u. But obviously we have no log here, right? Next, if you have an inverse function in the integrand, you will let u be the inverse function, but none of these functions are inverse functions, so that's not helpful. Next, if you have an algebraic expression or an algebraic function in your integrand, x squared is algebraic. So expressions like x squared or x cubed or square roots, those are algebraic expressions. So I think my choice here will be to let u be x squared. Okay, and then that means automatically, right, that dv is going to be whatever is left over. So that will be sine of x dx. Remember, the dx always goes with the dv. Now, see, once you have determined u and dv in the integration by parts process, now next you have to figure out what du is, and you have to figure out sort of the opposite here, what v is, right? You know dv, you want to find v, and you know u, you want to find du. Well, finding du is really, should be pretty easy, right? Because the derivative of u with respect to x here is going to be 2x, and now just solve this for du by multiplying both sides by dx. So you get du is 2x dx. All right, so that was easy. The hard part here, of course, is going to be finding v. But remember, v is the antiderivative of dv, and so that means it's the antiderivative of sine of x dx. What is the antiderivative of sine of x? We hope that's easy, and sure enough it is, because the antiderivative of sine of x is going to be minus the cosine of x. Be careful about that. Minus the cosine of x, right? Because remember, the derivative of cosine is minus sine of x, so the antiderivative of sine of x will be minus the cosine of x. So now you're in great shape, right? You have the du and you have the v, so you can fill them into your integration by parts formula. Remember, the integration by parts formula says what? I already started writing it down wrong, right? The integration by parts formula says that the antiderivative of u dv is equal to u times v minus the antiderivative of v du. So just fill things into this formula, right? So the antiderivative of x squared sine of x is going to be u times v. So u is x squared times v is minus the cosine of x, and then minus the antiderivative of, let's see, what was it now? V, right, times du. So v we know is minus the cosine of x, right? And du is 2x dx. Well, let's take care of a little bit of these. These minus signs are kind of messy here. So I have minus x squared times the cosine of x, right? I'm just going to put this minus in front. And these two minuses can cancel each other, right? So you get plus, and then the antiderivative of plus, the antiderivative here of, let me also factor out this 2 as well. So you get plus 2 times the antiderivative of x. I'm going to write the x in front of the cosine. So x times cosine of x dx. So if we can integrate x times the cosine of x dx, then we're done. Okay, now that is easier said than done, though, integrating x times the cosine of x. So we might think that we have reached an impasse here and that we had made the wrong choice for u and dv, but we didn't. We made the right choice for u and dv. What we're going to have to do here is use integration by parts a second time in the same problem. Okay, so we used integration by parts once to start finding this antiderivative, and now to finish finding this antiderivative, we're going to have to use integration by parts a second time. This is called iterated integration by parts, where you use integration by parts twice in the same problem. But the process is, of course, exactly the same as before, so we're just going to carry it out a second time. All right, so again, I'm trying to find the antiderivative now of x times the cosine of x. All right, so let's pick the u and the v again. All right, so well, let me use my Liate process once more, right? So my Liate process, here it is, right, says if I have a log, I'll let that be u, no log. If I have an inverse function, I'll let that be u, no inverse function, right? If I have an algebraic expression, I will let that be u. Oh, x, though, plain old x is an algebraic expression. So there we go. I'm going to let, in my second application of integration by parts, I'm going to let u be x. That means then that dv is going to be everything that's left. I'm not leaving myself enough room, so let me leave myself enough room here. Okay, so I'm going to let u here be x, and then dv is going to be cosine of x dx. And now let's just repeat this process, right? So first, let's find v. V is going to be the antiderivative of dv, which is cosine of x dx. And what is the antiderivative of cosine of x? Not the derivative, but the antiderivative. Oh, that's so easy. That is sine of x. So here we've got the v, right? Now, what about the du? Well, if u is equal to x, that means that du dx is equal to 1, or multiplying both sides by dx, we get du is equal to dx. Oh, great. So now, to find this antiderivative, we're going to, again, use that same integration by parts formula. All right, so let's start filling stuff in. Be careful that you don't write things down incorrectly, though, okay? So you have minus x squared cosine of x plus 2 times this antiderivative. But what is this antiderivative going to be, right? According to the integration by parts formula, see, this is u dv, right? X is u, and dv is cosine of x dx. So according to the integration by parts formula, that would be equal to u times v, right? So it would be x, which is our second choice of u, times our second v, which is sine of x, minus the antiderivative of v, which is sine of x, right, times du. But du is just dx, right? See, du is dx. Remember, this is v is sine of x. U here is x, and v, again, remember, is sine of x. So, I've got a big expression here, but let's just keep copying it down correctly. And now I just have to integrate sine of x. But it seems like we did that, right? Just a moment ago, we integrated sine of x, didn't we? Yeah, and it turns out to be, that's minus cosine of x, right? So you have minus and then minus a cosine of x. Oh, wow. And now, finally, that's it. You can see no more integrals left, right? So you're done. This is the antiderivative. Now you can add your arbitrary constant on. Let's simplify this a little bit. So I have minus x squared times the cosine of x plus, let's distribute this 2. So I have 2x sine of x and then plus 2 cosine of x and then plus the constant. So there we have it. Ooh, all the way, got to go all the way back to the top, right? The antiderivative of x squared sine of x, that turns out to be all of this expression here. Minus x squared cosine of x plus 2x sine of x, and then plus 2 times the cosine of x. So notice in this problem, we got to apply integration by parts twice in the same problem. And that will happen sometimes. That, again, is called iterated integration by parts. So that's going to show up at least a couple of times, I think, in your homework, right? Okay, about integration by parts. All right, so remember, I have not posted that homework yet, but I will post that shortly. We have one more example to do, which we'll take up in Monday's lecture, just as kind of a refresher on integration by parts before we start our next integration technique. And this is a really cool one. We're going to find the antiderivative of secant cubed of x, okay? And we're going to do that by integration by parts, but sort of, again, a little bit more sophisticated application of integration by parts. All right, so again, remember to visit my virtual office hours. Look at the announcement in WebAssign right on the right-hand side of the WebAssign page. That gives you all the information. Or visit Taylor's Zoom SI sessions. You can find that announcement of those instructions for visiting those sessions are in Blackboard. All right, and keep up with your homework dates. Monitor those closely and monitor emails from me, correct? And I will see you again on Monday, I think. All right. So good luck with your homework and good luck staying away from the virus. And so wash your hands, right? Okay. Talk to you guys later.